let's take a look at 2 to the third equals 8. Let's look at the anatomy of this. So we have the base, 2, raised to an exponent, 3, and that equals 8. We raise 2 to the third, that's 8. So the 2, again, is called the base, and then the 3 there is called the exponent. Okay, let's look at these in example 1. We have 3 to the x equals 9. So let's just kind of take a look at this and see if we can figure out what x is just by looking at it. So not actually solving an equation, let's just look at it and see if we can figure out what x is. So we're going to have to raise 3 to some power to get 9. Well, that's to the second power. So 3 squared is 9, so that means here x equals 2. We go to the right, 2 to the fourth power is 16. So that's 2 times 2 times 2 times 2. So x has to be 4, because that's the power we have to raise 2 to get 16. 5 to the fourth is 625, so here x is 4. And then if we look at this last one, 2 to the x equals 6. Well, we don't really have a good way of getting that. In fact, we don't have a way of getting that until this lesson. So this lesson is about how to solve that equation right here. 2 to the x equals 6. So this is a function that we can use that will allow us to solve that equation for x. So if we look at the equation x plus 2 equals 6, in order to solve that, we need to subtract 2. We need to undo what's done to x. So if we add 2 to x, we need to subtract that to undo it. If we have 2 times x equals 6, we have to we have to divide by 2 to get x by itself. If we have x squared equals 6, we need to undo that by taking the square root. And so here, in order to undo that 2 to the x, we need to do what's called taking the log base 2. And since the exponent here, again, has a 2 as the base, this logarithm has 2 as the base as well, so those bases will undo each other, and we'll just be left with the exponent x. So this right here, x equals the log base 2 of 6, is the solution to that equation. We'll talk about what that means and how that works in this lesson here. All right, we can switch back and forth between exponential form and logarithmic form, meaning having it written as an exponent, such as 2 to the third equals x. We can switch to this form here, the log base 2 of 8 equals 3. So what this logarithm does is it gives us the exponent. So what this says is the base, we have a base 2, so it's asking what power do we need to raise 2 to get 8. And that power is 3. Look at the second example, 4 to the 0 equals 1. We can rewrite that as this on the right here. Log base 4 of 1 equals 0. So this on the left side is asking what power do you need to raise 4 to get 0? I'm sorry, what power do you need to raise 4 to get 1? That power is 0. 1/4 to the negative 1 equals 4. So on the right side, the log base 1/4 of 4 is negative 1. Because again, negative 1 is the power that you need to raise 1/4 to get 4. There's 2 common logarithms that you're going to want to know. One of them is the logarithm of 1. Doesn't matter what the base is. The logarithm of 1 is always 0, regardless of the base, because again, anything that you raise to the 0 power is going to be 1. So if we have, say, the log base 3 of 1, well, that's 0 because 3 to the 0 is 1. And then we have logarithms with logarithms of b with base b. So this is easily shown with an example, I think. So if we look at the log base 5 of 5, that's 1, because again it's asking what power do we need to raise 5 to get 5? Well, that's 1. 5 to the first is 5. Looking at example 2 here, let's switch these to exponential form. So we have a log base 3. So that tells us that 3 will be the base of the exponent. And remember that the logarithm gives us the exponent, so on the right side of the equal sign, that's what the exponent is. And then we say that's equal to what's inside the log. Over here, 14 to the 0 equals 1. Rewriting in logarithmic form, we're just going to go the other way. So the base of the power is now the base of the logarithm. So we have the log base 2 of the answer to the exponential equals the power. On the right side, the log base 5 of 125 equals 3. Again, because 5 to the third power equals 125. Let's go down to example 4 where we're going to evaluate some logarithms. All right, so the log base 4 of 64 is asking what power do you need to raise 4 to get 64? Well, that's going to be 3. 4 to the third power is 64. On the right, the log base 6 of 36, that's what power do you need to raise 6 to get 36? That's 2. 6 squared is 36. On the bottom left, what power do you need to raise 9 to get 729? Well, that's to the third power. So this is equal to 3. Then on the right side, bottom right, we've got the log base 5 of 0.2. So we need to think about how can we rewrite 0.2 as a fraction. Well, 0.2, that's 2/10, or we can reduce that to 1/5. So we can say the log base 5 of 1/5. That's what this is asking us. All right, well, 1 over 5, that's 5 to the negative 1. So the power here is negative 1. 5 to the negative 1 equals 1/5. There's some special logarithms that we're going to use quite often. These are two logarithms that your calculator has built into them. And so anytime you're dealing with logs with your calculator, you're going to have to use one of these two logs. There's something called the common logarithm, which is a base 10 logarithm. And we use this a lot because we use a base 10 number system, meaning we have 10 numbers, 10 digits. So 1 through 9 and then 0. And this is nice when you have a base 10 number system because we can often talk about powers of 10. We do that quite often. So this is called the common logarithm. The other logarithm that's often used is the natural logarithm, and this uses the natural base e, and we call this the natural log, and it's typically written just ln of x. So if we grab a calculator then, on your typical TI calculators that I have in my classroom here, the log is the button right underneath the second button. So we can type in log and then 8, and that will come out to approximately 0.9. We'll round it off to 0.9. Then it says check with the calculator. So to do that, we would just take this 0.9, raise 10 to the power of that, because again, this is the base 10 log. If there's no number for the base, it's implied that it's a 10. So I could write a little 10 right there if I want. So we would take 10 to this power, 0.9, and we should get about 8. It's not going to be exact because we rounded it off, but it should be close. Then the natural log e. So base e. We have a natural log of 3. So we'd hit the button right underneath the one we used last time, ln of 3. You should get approximately 1.0986. I'll do a few decimal places here. So then if we wanted to check this, remember that this is base e, and so we take e to that power, the 1.90986, that should give us 3. All right, so exponents and logarithms, they are inverse functions, which means they undo each other, they cancel each other out. And so if we do the composition of the functions, if we plug one into the other, it should cancel down to x. So let's give this a try. We have f of x, which is the log base 2 of x, and we have g of x, which is 2 to the x, so it's an exponential where 2 is the base. And so if we plug one into the other, if we plug, say, g of x into f of x, then we'll get this. So f of x is the log base 2 of x, but again, I'm plugging in 2 to the x for x. So we have the log base 2 of 2 to the x. Well, since the log is base 2 and the exponent is base 2, those bases cancel each other out, and we're just left with x. Again, if they're inverses, we should be able to plug them into each other either way. Plug one into the other, or plug first into the second or the second into the first. It won't matter, we'll get the same thing. So we should be able to take 2 to the x, but then instead of having x, we plug in the log base 2 of x. Well, again, since we have an exponent where 2 is the base, and we have a log where 2 is the base, the bases go away. and we're left with just the exponent. Example 6, we'll try a couple of these with actual numbers. So 10 to the log base 10 of 4. Well, this is an exponent with a base of 10 and a logarithm with base of 10, so the bases cancel out and we're just left with 4. On the right side, we have log base 5 of 25 to the x. Well, 25 and log base 5 won't cancel out, but we can rewrite 25 as 5 squared. So let's have 5 squared to the x and take the log base 5 of that. Using our exponent rules, we can multiply 2 and x. So we get the log base 5 of 5 to the 2x. And now we have the log base 5 and a base 5 exponent. So we can cancel those out and we're just left with 2x. All right, example 7. Find the inverse of the function. So remember that inverses, you switch x and y, and then solve for y. So let's put x where y is, and y where x is. And then I'm just going to cross out this original one just to keep straight in my head that this green one is the one that I want to use now. Okay, so we're going to need to rearrange this to get y equals something. So to do that, let's take the log base 6 of both sides. So we have this exponent with 6 to the y, where 6 is the base of the exponent. So let's take the log base 6 of both sides to get rid of that. So we'll do the log base 6 of x equals the log base 6, log base 6 of 6 to the y. All right, so then the bases will cancel each other off. The log base 6 of 6 to the y cancels away, and we just get y equals the log base 6 of x. That is the inverse function. On the right side, again, switch x and y. And then what we want to do is solve for y. Okay, so we have the log, natural log, which is base e. So if we raise each of these sides as an exponent of e, then the natural log and e will cancel out. So we can do e to the left side, and then e to the right side. On the left side, we're just left with e to the x. But on the right side, we have an exponent with base e and the log with base e. Those cancel out, and we get just y plus 3. Then all we have to do is subtract 3 from both sides to get y by itself. And so the inverse of that is going to be e to the x minus 3. All right, example 8, let's graph a logarithm. So this, again, will be the inverse of an exponential function. It will be the inverse of the function y equals 3 to the x. Just to remind you, that graph y equals 3 to the x looks something like this, very roughly. It has an asymptote towards the negative x values, asymptote at y equals 0, and then in the positive y values, it goes up very, very, very quickly. So it's going to be the inverse of that, which again means it's reflected over this line y equals x. So we're going to get the mirror image of that. Let's see how that works. All right, let's just make a table first. So we're going to get some x and y values. We got to be careful about what we plug in for x. Because remember, what we're doing here is we're asking what power do we have to raise 3 to get whatever x value we plug in. So say that we plug in 1 for x. So that's going to be asking what value or what exponent do we have to raise 3 to get 1? Well, that's to the 0th power. So 3 to the 0 is 1. Then again, we want to be careful here. So let's do powers of 3. Let's pick 3 for our next x value. Because 3 to the first, so y value is 1, that is 3. If we plug in 9 for the next one, 3 to the second is 9, so the y value is 2. So for this one, it actually might be easier to pick your y values first and think about what you need to, what you get from your y values for the x values. Then the next one we could plug in would be 27, and we'd get third power. 3 to the third power is 27. That one obviously will not be on the graph. So let's plot those 3 points. So we have 1, 0, 3, 1, 9, 2, and then obviously we can't do the last one. Well, that's not super specific of a graph. Let's maybe choose some smaller numbers here. Let's say that we get some fractions, like maybe 1/3 for x. Okay. So what power would we have to raise 3 to get 1/3? Well, it's going to be to the -1 power. So at 1/3, an x value of 1/3, we get -1. Add an x value of, say, 1/9, we get -2 because 3 to the -2 is 1/9. And then you can see this asymptote is going to form here, and so we get the asymptote going along the y-axis this time instead of the x-axis. And then it's going to grow very, very, very slowly as it goes to the right. Okay, now let's talk about the domain and the range. Well, for the exponential functions, the domain was all real numbers, right? So I'll sketch that red graph again. The y equals 3 to the x looks something like that. So the domain is all real numbers. We can plug in any real numbers there. And since the x and y switches for the inverse, the range here for the blue one, for the log, is going to be all real numbers. Domain, however, will be restricted, just like the ranges for the original function for 3 to the x. So the domain is only positive x values. We only have positive x values here. We never get to 0 because that asymptote gets, again, infinitely close to 0, never actually gets to 0. And there are no negative x values here. And you can see that just by looking at the graph.